This is going to be the lecture over Chapter 19, Section 5, Resistors in Series and in Parallel. Now, if you'll remember, when we discussed it with capacitors, in order to be able to get the capacitance of a particular sequence, uh, depending on whether it was in series or parallel, we had different formula configurations. And what you're going to find with resistance is that it's going to be a little bit um, different from capacitance depending on whether you're talking about series or parallel. So um, when several resistors are connected in series, the equivalent resistance is going to be the sum of each of those resistances. When several resistors are connected in parallel, the equivalent resistance is going to be given by 1 over that for all of those. What do we mean by series and what do we mean by parallel? Well, in series, as you might imagine, you've got 1, 2, 3, 1 right after the other. You don't have any divergent pathways. You have to go through all of those. Parallel gives the charge a choice. You can go through this one, or you can go through this one, or you can go through this one in order to get from A to B. These are considered to be in parallel. Let's take a look here in the section. So, when several circuit elements, like resistors, batteries, or whatnot, are connected in sequence, like this, we say they're in series. Since no charge accumulates anywhere between point A and point B, the current is the same in all of the resistors when they are connected in series. So you've got 4 different ways here of connecting 3 resistors. This is going to be in parallel. Again, you have several different pathways that this could go through. Now, you've got 1 resistor here, and then you've got a parallel situation in which you can go through either resistor 2 or resistor 3. And then you've got even another combination here where perhaps, this series of resistors is one pathway, and this is another pathway in a parallel situation like that. So being able to add all of those up can be a bit trying at times. So for any combination of resistors that obey Ohm's law, we can find a single resistor that can replace the combination and result in the same total current and potential difference. The resistance of this single resistor is called the equivalent resistance. And if any one of the networks that we saw above were replaced by its equivalent resistance, we could write it in such a fashion like this. Now, one thing I will note here about this parallel situation, each resistor provides an alternate path for current elements that are connected in parallel. Potential difference, the voltage is going to be the same across each element. In 1919C, the resistors R2 and R3 are in parallel, and this is in combination with series 1. So resistors in series. For series and parallel combinations, we've got several different formulas to deal with each. If they're in series, the current is going to be the same across all of them. But the voltage across each resistor is going to be different, and that is because the resistance here is going to change. Potential difference from A to B is going to be the sum of those quantities. And since all of these share the same current but different resistances, then you can see how that goes together. Taking the voltage divided by the current would actually get you the equivalent resistance. And so you can see they're in series how you add them together. The equivalent resistance is always greater than any individual resistance. Well, that should be the case. Now, for resistors in parallel, the potential difference between the terminals of each resistor must be the same and equal to this. So if we go back and we look at part B, where they're all in parallel with each other, the current for each one of those is going to be equal to the same voltage divided by the resistance of each. If we add together all of the currents, we can factor out the same voltage for each one of them because it's the same value. And then we just have the reciprocals of those resistances added together in sequence. If we take I divided by this, that is the same thing as our equivalent resistance, or 1 over that, then we can see this relationship. So it's a reciprocal relationship. relationship. So you're going to have several problems here to work through to get through with that. I encourage you to do so.